Okay, good morning, good afternoon, everyone.
Huh?
Can you hear me? Can you hear me?
Yes, doctor, we can hear you.
Okay. John Bong Kiam,
Yes, sir.
can you read questions on the screen?
Figure Q1S shows a unity feedback control system. The system is controlled using a simple proportional controller K. Given two open loop transfer function G1S and G2S as following.
Okay.
With the help of loop rocker sketch for G1S is equal to 1 over S cubic plus 6S square plus 45S. G2S is equal to 0.075 S squared plus S plus 1
The plus,
over
there is plus, Ada correct. Plus S plus 1.
over S cubed plus 3S squared plus 5S. With the help of rocker sketch for G1S and G2S, explain the stability of each system at infinity, which is K equal to infinity. Determine the closed loop poles of the systems G1S and G2S for K equals to 40. Give your comments based on the results obtained. B. Given a unity feedback control system as shown in figure Q1B. And G3S equals to 1 over S plus 1 times S plus 3 plus S plus 2. Based on the new dominant pole, SD new shown on the root locus of the system in figure Q1C, determine the PD controller for the system GPDS equal to K times X plus Z. Given that the system needs to operate at zeta equals to 0.59 and overshoot 8% equals to 10%.
Okay, so this is the figure QC. So for this semester is during COVID time. So only one test. So Q1 10%, Q2 10%. So for Q2, we will not discuss because it is frequency response. So we just discuss Q1. Okay, this is exam test was during the COVID time. Right. So we go straight away to the solutions. Okay. So you are given G1, 1 over S cubic plus 6S squared plus 45S. Okay. And then G2 is 0.075 S squared plus S plus 1 divided by S cubic plus 3S squared plus 5S. Yeah. Okay. So find the roots. Okay. It is 0, -3 plus minus j6. We have 3 roots, and this one, the roots is 0 and minus 1.5 plus minus j 1.66. Okay. Then we sketch the root locus. Okay, so for G1 and G2. Okay. So the positions of the poles are here, here, and here, roughly. Okay. Then the shape is one is over here, ended at infinity. The other one is here, ended at infinity. And the last one is zeros, ended at infinity. So we have a 3 root locus path, okay, for G1. And then for G2, okay, so we label the locations. We have poles at the origin, and then we have 2 open loop zeros, okay. We have 2 open loop zeros. And don't forget there is a complex conjugate poles near here, okay. Okay, 0, -1.5 plus j 1.6. And don't forget this is for poles. And we have zeros over here, the roots, okay, which is minus 1.1 and 12.24. Okay, so this one no zeros, this one have zeros. Okay, so that's why you have 2 open loop zeros and 3 open loop poles. Okay, right, so as usual we sketch the root locus path. This one is our root locus 1 from poles to zeros. And then we have a complex conjugate poles, where this one we go here, end it here. Okay, and the other one is goes here and ended at infinity. And of course, we have a break-in point over there. Okay, can you see my drawing? Guys, can you see?
Yes, doctor.
Right. So the question said if the question said if with the hammer explain the stability of system, i.e. k towards the infinity. Right. Sketch for G1 and G2 there already explain the stability of each. Okay. So can you see the explanation there? Okay, so if you look here, k here equal to 0. Okay, until here, k critical. Okay. So this is the stability region. Okay. And from here, k equal to 0 until here. So this is the stability of the region. Okay. So once it passed to this area, so it's not stable anymore. So we can discuss that. So if K given as 40, so the G1, close loop lah, G1 to T1, okay. So T1 will become, this one is open loop, and this one is closed loop, okay. So this one will be G1, 1 plus G1. So the closed loop for system G1, okay, is 40 S cubic plus 6S square plus 45S plus 40. Because K 40 is the gain. Then for the G2, go to the T2. T2 is the closed loop. So G2 1 plus G2. So that's why T2 will become 3S square plus 40S plus 40 divided by S cubic plus 6S square plus 45S plus 40. Okay. So what can you say here? What is the observations? So we observe T1 and T2. Okay. T1 and T2. So you can see that the characteristic equation is the same. Am I right? Yeah, it's the same. And when the characteristic equation is the same, meaning that the closed loop poles also similar, okay? And both are third order system, okay? So we can observe here, you can write your observation. So this kind is a theory question. You have to give your observations, okay? Based on the calculation and derivation that you make just now, like I show you. So you can say that both systems, okay, have similar characteristic equation. I.e. S cubic plus 6S square plus 45S plus 40 equal to 0. So when you set characteristic equation, it must equal to 0. And then what else? Both have similar roots or closed loop poles, okay? I.e., so when you use your calculator for this characteristic equation, so you will get -1 minus 2.5 plus minus J 5.8. Okay. What else? Both systems are third order system, higher order, third order system. And the difference is T1 consists of pole and no zeros, no zero. While T2 consists of poles and zeros. So that is the difference. Okay. Pak Izzuddin, apa bising? Pak Izzuddin.
Sorry, Doctor.
Fokus lah. Tolong kau buat test. Right. So give your comment based on the result obtained. All right, okay. So and then the next one is this one, G3. Okay. Okay, so G3 is given as S plus 1, S plus 3, S plus 15, based on the new dominant pole, SP new, shown in the local system. In figure Q1C, determine the PD controller for the system. Okay, GPD is K S plus Z, given the system needs to operate at 0.59. Fazudin, tolong kira kan angle. Inverse cos 0.59.
53.84 degree.
53.84.
84.
Right. So there you are. Okay. The SD new. So we want the system base operate at the SD new. So when we use the protector, 53.84 is somewhere here. Okay. So this is the zeta 0.59. Okay. So what is the point over here? Okay, so the point over there is 1.75 plus J 2.39. And we want the new design, the new PD controller will operate at the given SD new, which is the minus 6 point. What is the value here? From your reading, 6.99 plus J 9.56. Okay. So we want at this new operating point. So design the PD controller. Right, so for Q2, G3 1 over S plus 1, S plus 3, S plus 5. So zeta 0.59 will give you theta
S plus 15.
S plus 15. 15, okay. So okay. Theta is 53.84 degrees. Overshoot is 10%. So PD controller. You have to design the PD controller, which is K S plus Z. Okay. We know that from the graph, zeta line intersect with RL at minus 1.75 plus J 2.39. But the new PD controller must operate at new dominant pole, which is dominant poles, i.e. from graph. Okay? If you read from the graph, the SD new is minus 6.99 plus J 9.56. Okay. So so we start with the find the settling time lah. Find the settling time. If you read the questions, okay. We didn't mention what is the new settling time. So okay, we just follow here. So we write the settling time, the old one, which is 1.75, the zeta omega n, 2.28 second. That the new one, ES new, is 4 divided by 6.99, okay, which is the new zeta omega n, which will give you 0.57 second. So you can see that the new one will settle faster compared to the old one, okay? So therefore, the omega n new, okay, 6.99, maintain the zeta line 0.59, so 11.847 radian per second. Then the new imaginary, which is omega d mu, is omega n 1 minus zeta square, which will give you plus j 9.55. Okay, 9.55, which is from the graph as well. So therefore, we draw the positions of the poles and zeros. Okay, so we have -1 over here, -3 over here, -15, and we put the zeros anywhere. Okay, and then the new dominant poles located at -6.99 plus J 9.56 or 55, both can be. Okay. And then as usual, you have to measure the angle. This PD controller is not simple and it's not straightforward SPI, okay? So you have to do some calculations on that. Okay, so theta 1, theta 2, theta 3, and theta 4. Okay. So measure the angle. So if you measure the angle, so theta 1 will give you 0.3 degrees. Theta 2 will give you 104.7. Theta 4 is 81 degrees. Okay. So this all are due to poles. Due to the poles. Theta 3 is due to the zeros. So therefore, theta 3, which is due to zeros, is summations of theta poles minus 180 degrees, which will give you 117. Okay. Then what is the location of the Z? So the location of the Z is here. This is the omega D, 9.56. And this is your minus Z. And this is your 6.99. Okay. And you have to find the alpha, the angle of alpha, because this part is 117 degrees. Okay. Okay, so what is alpha? What is alpha? Ahmed, Qadir, what is alpha?
Yes, doctor.
What is alpha? How to get alpha?
180 minus 170.
MashaAllah, tabarakallah. Okay, 63 degrees. So, we want to find the alpha because we want to know what is the distance here. Okay, the distance, let's say x. Okay, so therefore tangent 63 degrees is 9.46 and then x. Okay, so x is 6.99 minus z. Okay, so when you solve this, so you will get z is 2.12. Okay, so this is the poles, zeros for the PD controller. And the gain is k is equal to s plus 1 because of the pole, s plus 3, s plus 15 divided by s plus 2.12, the magnitude. Okay, then you insert the value there. Okay, the dominant pole value. Okay, so you insert the dominant pole value. Which is minus 6.99 plus j. So k will be 135.8. Therefore, GPD equal to k s plus z. 1313 meters. Okay. So Z is equal to KP, KD, which is equal to 2.12. Okay. So KD, this one will be the KP. Okay. This one will be the KP. So GPD is equal to 138.81 S plus 2.12. Okay. So that is your PD controller. Right. So that is the solutions for the Q1. For Q2, the second half of the test one during COVID time is on the frequency response. So I will not discuss this. I will include this in my lecture slides. Okay. So we'll discuss together later. So we go to the next one, which is this one, 2019. Siapa tu? Chun scan.
Yes, doctor.
Since you already coughed, can you help me to read question 1?
Okay. Analogy feedback system is shown in figure 2.1. Given that Gs k vector s squared minus 4s plus 8 over s plus 4s plus 10. For the given open loop transfer function, we have determined the following. The imaginary closing of the root locus of the closed loop transfer function has the gain at that closing. The arrival angle of the root locus of the closed loop transfer function, the breakaway point of the root locus of the closed loop transfer function is given as s equal to negative 6.05, and determine the gain at that point. Using the information gathered from 1 until 3, sketch the root locus of the closed loop transfer function. Hence, determine the rate of gain k for the underdamped stable system and critically damped system.
Right, thank you. Okay, so Again, this one, question 1 based on chapter 1. No plot given. Yeah, no plot given, eh? Okay, no plot given. How are we going to do this? Question 1. G K S square 4S plus 8 S plus 4S plus 10. Okay. So find the closed loop lah. Because you want to find the intersection kan with the imaginary axis. G 1 plus G. So the closed loop will be K S square 4S plus 8 K plus 1 square plus 14 minus 4K plus 8K plus 14. Okay. And then after you find the closed loop, find the characteristic equations. K plus 1 square plus 14 minus 4K plus 8K plus 40 equal to 0. Can. So what is the next step? What is the next step? Can we mock? What is the next step? Tak datang. Ni siapa pula lah nama tulis nama Cina ni? Tan Yajian. Tan Yajian.
Yes.
What is the next step?
The graph
This
is
one, second
is
step, third step, step number 4,
draw a table.
growth width table.
Yeah.
Okay. So K plus 1, 14 minus 4K. 8K plus 40, 0, 0, 0. And what is here? Noah, what is the question mark, guys? Noah, absent. Absent.
Me, doctor.
What is there over here? Can you see the dot?
Yes.
Oh.
Uh, 14 over 4K.
This is what you mean?
Yes, doctor.
Okay. So it is 8K plus 40, yeah. Correct. Hello?
Yes, doctor.
Ah. Yeah. So for the first column, growth width must be greater than 0, lah, positive. Okay. So find the range of stability. So range of stability is from the first column is 0, K, 3.5. So if K is equal to 4, is it stable or not stable?
Not stable.
Not stable, okay?
Not stable. Less
Yeah.
than 5.
Okay. If K is equal to 1. Stable or not stable?
Not stable.
Noah said not stable. Astaghfirullah.
Stable.
If K equal to 1.
Stable.
Stable or not stable or no?
Stable.
Stable, okay. And then if K is equal to 3.5, stable or not stable?
Not stable.
No,
Stable.
no.
Not equal.
Marginal stable. Repeat,
Margin.
marginal stable. So it will give you the K critical gain, okay? So use the even equation, which is from RH table. What is the even equation? Shui. What is the even equation from the root table? Datang. Lo Ji-Huan.
Hello, doctor.
What is the even equation
Even equation.
from the root Lewis table? This one, sk plus 1 s square plus 8k plus 40 equal to 0. So this one we call as the even equation. Okay.
Oh, okay.
So k is k critical is 3.5. Insert inside. Okay, so when you insert inside, so it will become 4.5 s square plus 68 equal to 0, and s is equal to plus minus j 3.89 radian, sorry, 3.89. So the intersection of RL and imaginary axis is S is equal to plus minus J 3.89. So what is the omega D? The frequency of omega D. Jin Cheng. What is the omega D, the frequency of the damn natural frequency? If the intersection is 3.89. Tak tahu. Li Jun?
Yes.
What is omega D? If the intersection is plus minus J 3.89.
Square.
Oh, kat mana ni? Jauhnya. Jenny Chua, what is the omega D if intersection is plus minus J 3.89? Jenny tak datang. Wong Jojin,
3.89 radian per second.
3.89 radian per second. Thank you. Okay. So students still don't understand. Don't know why. Maybe not focus. Too many holidays. Too much hari raya. Okay. What is the arrival angle of the root locus? Okay. Arrival angle. So we have to plot and see Okay. So kita kena plot. Okay. 2 J2 minus J2. Okay. Then minus 4. Okay. So the shape will be okay. And so this one will be the break. Okay. So we want to find the arrival. Because why arrival? Because we have a complex conjugate 0. Okay. Okay. Right. So we label. So this one is theta 1. This one is theta 2. And this one is theta 3. And this one will be the theta A, the arrival angle. Okay. So what is the formula? What is the formula? ISS Yemen. Who is this? Who is this? The ID is ISS Yemen. Undercover, agent undercover. Sun Jin Liang. What is the formula for the theta arrival?
Delta A
1 plus theta 2 minus theta A plus theta 3, 180 degrees. Okay. So theta A is theta 1 plus theta 2 minus 180 degree minus theta 3. So theta A is equal to 117.9 degrees. So this one you have to calculate by yourself. Yeah. This one is easy. This one is 90 degrees. Okay. This one you have to use the Pythagoras theorem. Sorry, trigonometry. Okay. If you don't understand, you have to go to the school form 3 to calculate the trigonometry. Part 3, breakaway point. Plot is not given. How are we going to find the breakaway point? Yep, Sun Yu. Yep, Sun Yu tak tahu. Mariam? How you?
Ada.
Jawab lah nama budak saya tak. Kalau tak sahut, saya padamnya mah. Tak datang. Is you differentiation, alright? D per
Yes,
D
yes.
per D per ds, correct? Huh? K equal to 1 D per ds. This one lah. S square minus 4s plus 8 s plus 4 s plus 10 must equal to 0. So this is the formulations to get the breakaway point. Okay. So when when you differentiate this one, so you will get the. Why don't we try? Okay. This one is s squared plus 14s plus 14, correct? Sun. Yep, Sun Yu, correct.
Yes, correct.
So 2s plus 14 s square minus 4s plus 48 minus 2s minus 4. Kan? Over s square plus 14s plus 40 equal to 0. So you simplify this, okay? You simplify that, then you will get s minus 6.05, okay? It is a quadratic equation, and you have two roots. You only choose only one answer, which is relevant. Minus 6.05, and the gain at the breakaway point is s plus 4, s plus 10, s square minus s. Insert this value inside the formula of gain. So you will get 0.1177. Okay. So the shape sketch as before, which is this one. This one, okay? The sketch. That is part number 4. And what is the range for K for underdamped stable system? What is the range? Miss Tang Hui Ting. Range of K for underdamped stable system. Tang Hui Ting? Tak datang. Tak datang. Mariam? Hello, Mariam.
Yes, doctor.
What is the range of underdamped stable region? You have to find the gain here. The gain here, K critical. And the gain here, K BAP. We already calculated that. Okay. What is the K critical, Mariam? K critical.
3.5.
3.5. Where do you get it? Yeah.
The previous side here.
Yeah,
Yes.
3.5, man.
Yeah.
3.5 and KBAP?
Was 0.1177.
0.1177. So the range will be KBAP less than K less than K crit. Okay, so that is the answer. Question number 2.
How about critically damped, the range?
Critically damped.
The previous question.
Which one?
Same question.
This
It
one.
asks us to find the underdamped and critically damped
No, the gain for underdamped system.
And critically damped. We
And-
miss critically
and
damped.
critically damped system. For underdamped stable system and critically damped system is zeta equal to 1. Kan? Zeta equal to 1, so you have to find the K. So, and the critically damped system, zeta equal to 1. So where is zeta equal to 1? Zeta equal to 1 is over here. Okay, so this one is on this part. Okay, critically damped when zeta is equal to 1. Because here, over here is zeta equal to 0. On this part is zeta equal to 1. Okay, so the gain will be from here to here. Okay, so we can take this number, minus 10 and 4, insert inside the gain formula. Okay, then you will find the critically damped gain. Okay, did I answer your question?
Yes.
Add S minus 10 and S minus 4. Okay. Pak Izzuddin, baca soalan nombor 2.
A closed loop unity feedback system as in figure Q2 has a root locus as shown in figure Q2.2. One designed a PD controller to yield a damping ratio of 0.59 with a 3-fold reduction in the system settling time. 2, for the compensated system, determine the peak time and the steady state error. Third, sketch the step response of the compensated system.
Right. Thank you. So this is the given. GS is not given. What is GS? GS is not given, so we have to extract out from here. So this is your minus 12. Minus 12. Ini berapa ni? Minus 1. Minus 3. Kan? So the GS will be K S plus 1, S plus 3, S plus 12. Okay. And from here, you already know that the breakaway point minus 2. And the intersection, help me. Ahmad Salim, help me. What is the value there?
7. About 7.2.
7.2. 6. In the middle. 7.2. Okay. Okay, خلاص. شكرا حبيبي. Okay?
Left.
Huh? Correct? Okay. So zeta 0.59. TS neo 1/3, 3/4 lah. TS whole. So theta will be 53.8 degrees. Okay. We draw the line lah. You draw the line. Okay. So I clear this one first. Okay, so we draw the line. And this is the dominant pole. Okay. So the dominant poles will be minus 1.8 plus J 2.2. Okay. So the TS all is 4 divided by 1.8, 2.22 seconds. And the TS new is 1/3, 2.22, which is 0.74 seconds. So this is our target. Okay. Our target to find. Okay. So therefore, TS new 0.74 is equal to 4 divided by real new. So the real new will be 5.4, okay, which is equal to zeta omega n. Yeah? And omega n will be 5.4 divided by 0.59, 9.15 radian. And then find the imaginary new, which is a j omega 1 minus zeta square. So you insert inside 9.15, 1 minus 0.59 square, 7.39. Okay. So our new dominant poles is SD 7.39. Okay. Which is located on the S-plane somewhere here. Okay. And then this is your minus 12. This is your minus 3. This is your minus 1. And this is the zeros that you want to calculate. Okay. Then find the angle. Okay. So use the formula theta 1 plus theta 2 plus theta 3, theta 4, 180 degrees. So the theta 4 will be, theta z. Theta 1, theta 2, theta 3. Okay, so theta 4 is the theta z, which is 97 degrees. Okay. Then find the z values by calculating the distance. This one is omega d. Okay, find this distance, which is x. So tangent 180 degrees minus 97, 7.39 divided by x. Okay. So z, you will get 4.49. Okay. So the GPD is equal to Ks plus 4.49. But you have to calculate this gain value, okay, which is equal to 89, okay, i.e. you replace with the just now s plus 1, s plus 3, and s plus how much? 12. Divide by the new zeros. Okay, so you get 89. Okay. The S value, S is the dominant pole, the new dominant pole, which is this one. This one. Okay, insert this value inside here, then you will get 89. So 89 will be the gain of the PD controller. 89. S plus 4.49. And the new peak time will be pi divided by imaginary, which is 7.39, 0.43 seconds. And this system is type 0. Okay, so you have to calculate the KP. And the KP will be limit S to 0, 89 S plus 4.49. Divide by S plus 1, S plus 3, S plus 12. So KP is equal to 110.9. So the steady state error will be 1 over 1 plus KP. 0.009. Almost 0. Okay. But some values. And then we can plot the shape of the response. Rahma, can you tell me what is the shape of the response? Rahma, answer. Okay, something like that. Okay. All right, I think that's all. It's 1 o'clock already. So thank you for your attendance. 53, 52, meaning that 6 students is not attend the class. Any question? Any question? David Fan, any question?
No question.
Abdullah Shatari,
No question, Doctor.
لا مشكل.
لا مشكلة.
لا مشكلة. Solihin, paham? Tak paham tengok balik. Tak paham, if you don't understand, you look at the YouTube lah.
Okay. Thank you.
Then you like lah. Huh? You like that? Solihin, you like tak?
Apa itu?
Like.
Like. Oh,
YouTube.
tak tengok lagi tak start study lagi. Nanti saya start study saya tengok saya like tu. InsyaAllah.
Alright, there is no question. I see you next week on Monday with the PID controller. The new update notes will be given later. Okay? Thank you very much. Bye.
Thank you, Doctor.
Thank you.
Doctor, next week class is also online, right?
No, face to face.
Face to face. Oh, okay.
Face to face. Online class. No more online.
Oh, okay.